So in many back surgeries, a spinal probe is used to help the surgeon position a screw into the vertebrae. The current probe is essentially a giant metal toothpick.
We invented the AccuSpine, a low-cost surgical device used in spinal surgeries to accurately place screws within the spine.
So what we decided to do is add brains to the system. The device uses an electromechanical feedback system that allows the surgeon to know exactly where he is in the spine, and it prevents breaches so that the patients don't come out of the surgery with paralysis.
This device is safe for patients, fast for surgeons, and cost-effective for hospitals.
So right now we're in the process of refining our invention, pursuing patent rights, and going through FDA regulations to get our product to the market.
My name is Eklavya Singh.
And I'm Rahul Mukherjee, and we are PhD students in RPI in the Department of Mechanical Engineering.
Then we decided to try to commercialize graphene and use it for lithium-ion batteries to make the next generation of better performance energy storage device.
The primary challenge, and that is a challenge with any nanomaterial, is scaling up the technology.
What our technology provides is a lithium-ion battery with excellent energy densities, which is around 2 to 3 times higher than commercial lithium-ion battery applications.
Currently, lithium-ion batteries use lithium cobalt oxide cathodes. By using an all-carbon chemistry, we're able to reduce the cost, eliminate these toxic and expensive metals from the battery.
It's a lithium-ion battery that can sustain a device for a longer period of time on a single charge.
Eventually, we reach our ultimate goal of having these graphene-based batteries in electric vehicles.
Hi, I'm Katherine Cagen from Harvard University. There's a lot of room for improvement in the technology that visually impaired students use. My invention is going to change the world by helping visually impaired students access educational materials like graphs and diagrams. My invention is Ferrotouch, a refreshable tactile display technology. By using a grid of electromagnets that can be turned on and off, the ferrofluid will form a raised shape. A visually impaired user can then feel that raised shape through a thin membrane. My strategy is to create a low-cost open-source hardware kit for my Ferrotouch display to prove that there are people out there who want this technology.
Hi, I'm Tasha Silica. I'm from Stony Brook University. My invention, known as Immunomatrix, is a sophisticated Band-Aid that offers the same protection as a traditionally administered vaccine. The Immunomatrix is composed of a three-dimensional mesh of nanofibers. Inside of those fibers are antigens, which we encapsulate during the process of electrospinning. It delivers large molecules such as antigens through the top layers of the skin and evoke an antigen-specific immune response. What keeps me up at night is making sure that this technology is sooner or later brought to clinic. This is basically my invention. It could be as easy as putting on a Band-Aid.
There are approximately 200,000 shoulder surgeries related to rotator cuff repair in the United States each year.
Failure rates are between 20 and 90%. The Inceda Pro will significantly reduce those failure rates. Our device allows the doctor to deliver a surgical graft arthroscopically.
Because of the small size of the cannula used for arthroscopic shoulder surgery and the size of the graft, at times it felt like we were trying to stick a square peg in a round hole.
You're going to attach a square graft to those arms. The arms are going to close and the graft is going to be folded up.
Once it is open, the surgeon can use the handle to position the graft in the proper placement for suturing. And these inventions are changing people's lives.
We're from the University of Utah, and we're finalists in the 2014 Collegiate Inventors competition.
When we first learned that there's over 100,000 deaths due to bloodstream infections caused by catheters, we were shocked.
Our invention works by utilizing a high-intensity visible light that we have proven to effectively kill bacteria.
Through in vitro laboratory testing, we sat down with lots of different bacteria and really tried to understand how our light would kill them the best way.
We've created a simple device. It turns on with a simple push of a switch, and it propagates the light that effectively sterilizes from tip to tip, inside and out.
We think within about 12 to 18 months, we'll actually be through the FDA, and at about that 18-month mark, we're going to begin marketing and selling our device to hospitals.
Hi, I'm Xing Liao from Northwestern University.
Hi, my name is Keith Brown. Imagine if you could make a nanostructure with the same kind of whimsy that you can print a document. Allow me to introduce you to the Desktop Nanoprinter version 1. 3 critical components to this. The first is a projector. This allows us to project light down to very small features. Now this is projecting onto our pen array. It's an array of about 10,000 small pyramids, each with small holes in the gold. We take an image, we load it into the software, and it's going to break that image up into different pieces that each pen in this array is going to write. Simply hit go. This will allow anyone who's interested to be able to make nanostructures.
Hi, my name is George Herrera. I'm from Stanford University. My invention is of a device for carrying out complex medical assays. We're particularly interested in developing a way to diagnose neonatal sepsis rapidly. It's hand current driven and therefore requires no power. The microfluidic tip has a series of channels in them. Punctured tape has a series of holes which determines through the turning of the gears, fluids are driven in the microfluidic tip. I'm really motivated and passionate about finding ways in which we could address some of these problems that face so many people.
Hi, I'm Eric Ronning. And I'm Will Doniger. And this is Brian Pekron. And we're students at the University of Wisconsin-Madison.
The Remex is a technology for technology. High throughput, gentle flow static mixing doesn't exist right now, and that's what the Remex is. It's a mixer that doesn't have any moving parts, but is extremely gentle on the reactants. This enables live cell applications, like in the case of biofuels and even cancer research, and can be that enabling piece of technology as they make their way from lab to market.
Hi, I'm Alex Nektow from the Rockefeller University, and I'm a finalist in the 2014 Collegiate Inventors competition. What I've been doing in the past few years has been looking into new ways to gain fundamental insight into how the biology of the brain works using technologies and tools that I myself have built. The brain is comprised of numerous interacting neural networks, which are large sets of neurons that communicate to each other. RetroTrap is of particular importance to the field of neuroscience because it enables us to functionally dissect neural circuitry based on who these different populations talk to. One of the major goals of President Obama's BRAIN initiative is to understand the brain through developing novel technologies. RetroTrap is one of these technologies.
Spectrum is a full color device, and it's made for FDM 3D printers.
The ability to generate any object in whatever color you want, this is unprecedented in the industry. What we're doing is essentially interfering with the plastic. We're coloring it right before it gets to the nozzle, and we do this with two ways. First is the use of a solvent dye, which deeply incorporates itself into the plastic and leaves the dye behind while evaporating the liquid away. And second, it's with computer-controlled precision, and that's the dye applicator we're using. Engineers can make precise multicolor objects to show clients our vision is to have it be one device, have this shrunk down and fit within the printer and work seamlessly for our users.
Hi, I'm Keith Herrera. I'm a postdoctoral fellow at MIT, and I'm a finalist in the 2014 Collegiate Inventors competition. In summer 2012, I was approached by one of my best friends that now works in real estate for a major US fast food company. He said, "Keith, can you come up with a new way to recycle styrofoam?" What I discovered was that this company's biggest waste product by volume was styrofoam. That this company's biggest waste product by mass was citrus rods. In my invention, citrine, I've developed a series of materials that are derived from citrus extracts. And the materials from this citrus extract can be either soft, flexible, or rigid. A second major part of this invention is the fact that citrine can also be used to recycle styrofoam and other plastic materials. And the applications of this sustainable material system range from medical technology to commodity plastics.
There are over 700,000 knee replacement surgeries performed every year in the United States alone.
Bacterial infection is the leading cause of premature implant failure.
This is a really big problem.
And costs the healthcare system roughly $400 million annually.
Our invention is an implantable medical device that is integrated into prosthetic knees.
When our device is activated, an LED shines light through the synovial fluid and a photodetector measures the degree of scattering present. The more white blood cells present, as in the case of infection, the more the light is scattered, and a signal is sent to the user alerting them of the presence of infection.
We think our device is going to revolutionize one of the biggest industries within medicine.
A lot of chemotherapy technicians and doctors don't know just how inaccurate their measurements of chemotherapy drugs actually are.
Volumetric is a device that allows you to draw and dispense precise and accurate amounts of fluid from a syringe.
A syringe just fits in it, and you pull it back to the desired amount, and it'll display the exact volume right here, and it increases the accuracy almost tenfold.
There's a capacitive distance sensor that is used and interpreted by a microcontroller to convert the distance to volume based on a set of coefficients that we determined experimentally.
We think that this is really gonna change the way that chemotherapy treatments are prepared.